We are given a binary tree and we are supposed to delete some nodes. The criteria for deleting some of the nodes is when the node value is part of this to-delete array. For example, this is our binary tree. This to-delete array has the value of 3 and 5. Once our node value is part of this array, meaning if it is 3 or 5, we are supposed to delete it. So we delete this node and this node. Then we found out once we delete this 3, we have 2 hanging roots or 2 new roots or disjoint union of trees. All of a sudden, we found new trees. We are supposed to return an array of all the roots. So in this case, we deleted 3, we deleted 5, we return 1, 2, 4, 6, and 7. What is the intuition for solving this problem? First thing first, in order to find the result, what is the result? The result is an array of nodes. So let's think of what are the criteria such that the node can qualify as part of the array. What is this result array? This result array is all the hanging nodes, meaning its parent just got deleted, or it is the very top level root, right? In this case, 1 is a very top level root. 6 and 7 are returned because the parent is deleted. Okay, so we can sort of formulate when we can sort of formulate a criteria when our nodes, when shall we push nodes to result array? It is when, oh boy, it is when its parent is deleted. In this example, 6, 7 parent is deleted, so the parent is 3 is deleted, so 6 and 7 are pushed to the result array or top level root. The other condition is the node itself must not be deleted. Meaning, if to-delete has the value of 6, then this 6 will not be part of the result array because the node itself is deleted. There's something else we need to do. As of now, we know a way to identify which nodes can qualify to be part of the result array. But there's something else that needs to be done, which is when you see when we are returning the root 1, we need to sever the link between 1 and 3, because 3, which is 1's child, is to be deleted. So we need to sever the link between the parent and child. In other words, separate the parent and the child. So how do we know? So how shall we separate the parent and the child? How shall we separate 1 and 3? There are 2 ways to do it, and I will go over both of them. The first way is to make the parent check the child. Have an if condition, let the parent check the child condition and see if the parent should abandon the child. The second way is by relying on the response from the child. If the child tells the parent to abandon him, then the parent abandons the child. This will be in the form of a return statement. a return value from a recursive function call. So let's go over the solution in C++ now. I will go over the solution in JavaScript later. So let's code C++ now. Let's first initialize the result array. And in order to know whether a node should be deleted, it must fulfill that the node value is not part of the toDelete array. So you may want to use a hash table, because it provides constant time lookup. So our hash table is called US. Now, since we want to do a recursion, we may need a helper function. So what should the return type be? As of now, we do not know yet, so let's just put void. We may change it later. Need hash table. We also need the result. All right. And let's call it. Okay, so we're passing in three things: the root, hash table, and the result, which we want to change. So the most important thing is to, in order for a root to be pushed to the result array, there are two conditions. Which of these two conditions are easier to code? This, right? The node itself must not be deleted. Let's just call it deleted, which represents this node is deleted. So you can just do a lookup to our hash table. So when the node is not deleted means not deleted, right? And its parent is deleted, or it is a top level root. Now, where do we get this information? We do not know this information. So why not just make one up? Let's call it PD. You know, our parent got deleted. So we can make use of it here. If I am not deleted and my parent got deleted, so we push the node to the result array, right? Res, so we push. Of course, since we added another parameter, we need to update this. Should this be true or false? This refers to the very top level node, because the very top level node does not have a parent, means it's kind of like its parent got deleted. So it's true. Then let's do its recursive call to the left and the right. Because of this, let's do a check. Left child. Now, what shall we pass down to our child for the parameter of parent deleted? When we are talking about parent deleted, and we are passing this parent deleted to our child, this parent is me. So I am passing in deleted, right? I am deleted is the same as saying my child's parent deleted. Let's do the right child. Okay, this code is not complete. I hope you can spot why it is not complete, but let's just print whether what kind of result this gives us. So we succeeded in something and failed in others. What we succeeded in is we have correctly identified what are the nodes that should be pushed to the result array. 1, 6, and 7, we succeeded. What we failed is to sever the link between the parent and the child. To be more specific, our root 1, we need to sever the link between 1 and 3 and 2 and 5, but we have not done so. Okay, so let's now do that. How can we sever the link between the parent and the child if the child were to be deleted? As I mentioned earlier, there are two ways to do it. The first way is to make the parent check on the child's values via if statement. The second way is the parent ask for the child's response via return value. Don't worry, I'll go over both of them. So the idea is after you go over the recursion on the left, you may have the parent may need to abandon the child. So the parent need to check if the root left does not exist, or the left child's value is part of the result array. I sever the link. Then you do it for the right also. That's it. I think we can submit this now. This is the first way. Check the parent check on the child's value. Okay, it's a typo. Now the second way is the parent asks for the child's response via a return statement. So let's delete this. What do I mean by that? So we are not doing void anymore. We can choose, a bool. You can also choose a tree node. Doesn't matter. I'm just gonna use a bool. So we are returning something. The child must return whether it is deleted, right? So just return deleted. Yeah, just return deleted. If the child is deleted, root left is null, right? If right child is deleted, right child is deleted. That's it. Of course, this is deleted. Now I'll go over the solution in JavaScript. Now let's move on to JavaScript. What I'm going to do is to copy paste my code from C++ because the algorithm is the same. We need a result array. We don't need a hash table and a recursive function call. So result array and a recursive function call. Now, we don't need all 4 parameters because in JavaScript we are gonna, put the function inside this function. So, but we still need root, we still need parent deleted. the hash table and the result array are not needed. So we have root and the parent deleted. Root and true, true. Okay, the first, if not root, return true. Deleted is true when root value is part of the toDelete array. If not deleted and parent deleted, result push. Do recursive function call on the left and on the right. Deleted. Copy paste. Return deleted. I believe this will pass. There we go.